Hi guys! Today we're going to talk about graphing functions and how the first and second derivatives can affect the graph of a function. I wanted to make this video because I want you guys to have the opportunity to go back and re-watch sections so that you can get the support you need for each individual piece. Truth be told, this lesson isn't new. We've talked about limits, we've talked about first derivatives, we've talked about second derivatives. What we've never seen is all of it culminating into one problem. And so this lesson can be kind of intimidating. And so hopefully this video and the opportunity to go back and forth and to rewatch will help lower that intimidation. Let's get started. I'm going to start with intercepts, as we usually do with graphing. A y-intercept would imply that x is equal to 0. And if x is 0, we would look at f of 0 is 0 times e to the 0. I'll go ahead and show my work. It should be 0. And so 0, 0 is the y-intercept for this function. We should check to see if there's any more x-intercepts, which would imply setting y equal to 0. And so we're going to try to see if f of x equaling x e to the x equals 0, and if x e to the x equals 0, either x is 0, we already knew that, or e to the x is 0. Now think about, when does e to the x equal 0? And you're right, never. Okay, e to the x looks like this guy right here. We know that will never cross the x-axis. So we have one x-intercept, one y-intercept, and I'm going to go ahead and draw a pretty crude graph just so I can piece together all of this information that we'll be collecting. Right here, 0, 0 is an intersection, and that's all we know so far. The next thing we should look at is the domain of the function. So if it helps to organize our information, the first thing we looked at is intercepts. The second thing we'll look at is domain. There's nothing you can't exponentiate, and there's no problem with multiplying these two terms, so the domain for f of x will be all real numbers. Okay, that's going to become important for step number 3, where we look at end behavior. Remember, back from Unit 1, the very beginning of this school year, to determine end behavior for a function, we should look at limits. And that's why I looked at domain before I looked at limits, because I don't know what the ends are unless I consider domain. And so here, the left end, we might say, is negative infinity, and the right end would be positive infinity. Let's go ahead and focus on this first limit. And so we would look at the limit as x approaches negative infinity of x e to the x. Now if we analyze this, maybe it'll help if I color code this. This term here is going towards negative infinity. And I need that color. This term here is going towards e to the negative infinity. And e to the negative infinity goes e to the infinity. That's what that negative means. And so that would look like 1 over infinity, which is 0. So right now we have negative infinity times 0, which we know is an indeterminate form. But I can't use L'Hopital's until I have it in either infinity over infinity or 0 over 0. Okay, so we can go back to section 4.4 and look at L'Hopital's rule. Harrington's unofficial rule of L'Hopital's: never move a natural log, which would imply always move an exponential. Let's reassess. This guy here is still going towards negative infinity. That didn't change. But now here, looking at this function as 1 over e to the x, if x is approaching negative infinity, then this would be going towards e to the positive infinity, which is going towards infinity. So now we have an infinity over infinity situation. Okay, I'm going to go ahead and apply L'Hopital's. Let's denote that with our L'H. Derivative of the top over derivative of the bottom. And if I reassess here, getting rid of that negative in the exponent, I would have negative e to the x. And if x is approaching negative infinity, this looks like negative e to the negative infinity, which we've already done up here. We saw that that was tending towards 0. So our limit here will be 0. Okay? In other words, as x gets very small, because x is approaching negative infinity, our y value is approaching 0. So I'm going to go back to our crude graph. As x gets very small, our y value is tending towards 0. What we don't know is whether or not it's tending towards this way or this way. So we have to keep our options open. This we're not really sure about yet. So hopefully further information will help us decide that. Okay, let's go ahead and look at the second end. That means I'm going to look at the limit as x approaches positive infinity of f of x, which of course would ask us to look at x e to the x. Let's not forget our equal sign. And if we assess x is going towards infinity, e to the x is going towards e to the infinity, which e to the infinity is going towards infinity. So I have infinity times infinity, which we get infinity. So what does that mean? As x is getting very large, our y values are also getting very large. So I'm going to go back to the graph, and we see that for very large x values, f of x values are getting very large. So we're going to see this motion in the first quadrant where the function is going up and to the right. So we can kind of get an idea that most likely this is going to happen. I'll do that again. From here to here. Maybe even if I highlight this, and I'm just kind of drawing a rough sketch. Okay. The reason I know that this cannot work, that f of x is approaching 0 from the third quadrant, is because, oh, well, I guess I don't know that. We could have actually done this. So there are my two options. I scratched that idea. We don't know yet still if f of x is going to approach from the top or from the bottom. Hopefully further information will get that out. Okay? So I had to correct myself on that one. Okay, let's start looking at derivatives. So I'm going to start with that original function, f of x. Let me rewrite it here. And we're going to look at first and second derivatives and see what's going to happen there. Okay, first derivative, using the product rule. And we can factor out an e to the x. And we're always interested when that first derivative is 0, which in this case gives us two equations to solve. E to the x will never be 0, and this one yields x is equal to negative 1. Okay? If I look at a sign chart for the first derivative, we would allow all x values, but here I'm going to block off a boundary at negative 1, and I'm going to look at what makes up f prime of x. It's the product of e to the x and 1 plus x. But e to the x is always positive, so I didn't really need that on my sign chart. 1 plus x will be negative to the left of its 0 and positive after. And we're multiplying the two together, so f prime of x is negative, then positive. And so what does that mean? If f prime of x is negative, that means f of x is going to be decreasing. And if f prime of x is positive, then f of x will be increasing. Okay, that implies to us that we're going to have a relative min. A relative minimum value at x equals negative 1. Let me go back to that crude graph. And I'm going to redraw just the pieces that we know. Remember, we had the x-intercept. We knew this was going to happen. We weren't sure if it was going to be this or this. Although now we know that we're going to have a relative minimum at x equals negative 1. Okay, so we see that right here, a relative minimum at x equals negative 1. And so at negative 1, I'm going to see a low point. So which of the two cases do we have to see? Okay, it's definitely going to be this guy, because in order for that to be a low point, we have to be coming from the third quadrant. So now we can kind of get an idea of what's happening here. Okay? So we have this idea where this function is going to live in the first and third quadrants. Notice this concavity shift that has to occur somewhere to the left of negative 1. And that concavity change would show us an inflection point, and that's going to require this second derivative. Okay, so I'm going to go back to our first derivative, which is right here. Okay, our first derivative was e to the x times 1 plus x. It's up to you whether or not you want to take the first derivative from here or from here. I usually tend to go up here, just because the more factored that function is, the harder the derivative is to find. So I'm going to stem from this function right there. Derivative of e to the x is e to the x. The derivative of x e to the x we already found, so I'm going to cheat. That's just f prime I'm just copying that down. So we get 2 e to the x plus x e to the x. And we want to know when that first or second derivative is 0. So we'll go ahead and factor. And we have 2 equations to solve. And so this would give me no solution. Here we have x is equal to -2. Okay, we'll look at the sign chart real quick. All real numbers, blocking it off at -2 this time. F double prime is a product of e to the x, didn't need that, 2 plus x. And so the second derivative is negative and then positive, which means that f of x will be concave down and then concave up. So we see that inflection point occurring at -2. Okay, but we've already had that idea that we were going to see an inflection point to the left of -1. Okay, so I'm going to now draw, hopefully, a not-so-crude picture of what f of x is going to look like. I'm going to show you all of the important parts. So here's my y-axis. Don't forget to label. We had the intercept. We had a low point. We had an inflection point. And I know that point can't be lower than this low point, otherwise we would have found a peak. And we know end behavior mandates that the function is going to increase all the way in the first quadrant. And we had an asymptotic behavior in the third quadrant. And there's my function.